Okay, hi. So we're up to Module 9 of ENSA, which is Quality of Service Concepts. All right, so we're going to look at the network transmission quality. We're going to look at traffic characteristics, queuing algorithms, QoS models, and QoS implementation techniques. Okay, so network transmission quality. Okay, there we go. When traffic volume is greater than what can be transported across a network, devices queue or hold the packets in memory until resources become available to transmit them. Queuing packets causes delays because new packets cannot be transmitted until previous packets have been processed. And the number of packets to be queued continues to increase. The memory within the device fills up and packets are dropped. One QoS technique that can help with this problem is to classify data into multiple queues, as shown in the figure. And so a device implements QoS only when it is experiencing some type of congestion. And so basically you have different priority queues. And so the highest priority queue will need to be empty before any of the medium priority queues. And then both of those need to be empty before the low priority queues packets are transmitted. Okay, so bandwidth, congestion, delay, and jitter. Network bandwidth is measured in a number of bits that can be transmitted in a single second or bits per second. Network congestion causes delay. Interface experiences congestion when it is presented with more traffic than it can handle. Network congestion points are ideal candidates for QoS mechanisms. The typical congestion points are aggregations, speed mismatch, and LAN to WAN connections, basically. So of course your WAN links are normally a lot slower than your LAN ones. All right, so bandwidth, congestion, delay, and jitter continued. So delay and latency refers to the time it takes for a packet to travel from the source to the destination. Fixed delay is the amount of time a specific process takes, such as how long it takes to place a bit on the transmission media. Variable delay takes an unspecified amount of time and is affected by factors such as how much traffic is being processed. Jitter is then variation of delay of received packets. All right, so there's code delay, the fixed amount of time it takes to compress data at the source before transmitting to the first internetworking device, usually a switch. Then there's packetization delay, the fixed time it takes to encapsulate a packet with all the necessary header information. Then there's queuing delay, the variable amount of time a frame or packet waits to be transmitted in the link. There's serialization delay, the fixed amount of time it takes to transmit a frame onto the wire. Then there's propagation delay, the variable amount of time it takes for the frame to travel between the source and destination. And then there's a de-jitter delay, so the fixed amount of time it takes to buffer a flow of packets and then send them out in an evenly spaced intervals. Okay. Packet loss. Without QoS mechanisms, time-sensitive packets such as real-time video and voice are dropped with the same frequency as data that is not time-sensitive. So when a router receives a real-time protocol digital audio stream for voice over IP, it compensates for the jitter that is encountered using a play-out delay buffer. The play-out delay buffer buffers these packets and then plays them out in the steady stream. So you can see variable spaces here while it's all consistent once it's been through that buffer. Okay, packet loss. So if the jitter is so large that it causes packets to be received out of range of the play-out buffer, the out-of-range packets are discarded and dropouts are heard in the audio. For losses as small as one packet, the digital signal processor interpolates what it thinks the audio should be, and no problem in audio is no problem is audible to the user. Sorry, when jitter exceeds what that signal processor can do to make up for missing packets, audio problems are heard. And so in a properly designed network, packet loss should be near zero. Okay, so traffic characteristics. So network traffic trends. In the early 2000s, the predominant types of IP packet were voice and data. Voice traffic is a predictable bandwidth need and known packet arrival times. Data traffic is not real time and has unpredictable bandwidth needs. Data traffic can be temporarily burst, as when large file is being downloaded, this bursting can consume the entire bandwidth of a link. More recently, video traffic has become increasingly important to business communications and operations. And so, according to the Cisco Visual Network Index, video traffic represented 70% of all traffic in 2017. By 2022, video will represent 82% of all traffic. Mobile video traffic will reach 60.9 exabytes per month by 2022. The type of demands that voice, video and data traffic place on the network are very different. So voice traffic is predictable and smooth and very sensitive to delays and drop packets. Voice packets must receive a higher priority than other types of traffic. So Cisco products use the RTP port range from 16384 to 32767 to prioritise port voice traffic. Voice can tolerate a certain amount of latency, jitter and loss without any noticeable effects. Latency should be no more than 150 milliseconds. Jitter should be no more than 30 milliseconds and packet loss no more than 1%. Voice traffic requires at least 30 kilobits of bandwidth. So basically, so the characteristics of voice traffic, it's smooth, benign, drop sensitive, delay sensitive, and UPD priority. So latency should be less than 150 milliseconds, jitter less than 30 milliseconds, and loss less than 1% bandwidth. All right, video traffic tends to be unpredictable, inconsistent and bursty. Compared to voice, video is less resilient to loss and has a higher volume of data per packet. The number and size of video packets varies every 33 milliseconds based on the content of the video. UDP ports such as 554 are used by real-time streaming protocol and should be given priority over other less delay-sensitive network traffic. Latency should be no more than 400 milliseconds, jitter should be no more than 50 milliseconds, and video packet loss should be no more than 1%. Video traffic requires at least 384 kilobits of bandwidth. And so video is bursty, greedy, drop sensitive, delay sensitive, and UPD traffic. And so your latency should be less than 2 to 400 milliseconds, jitter less than 30 to 50 milliseconds, loss less than, well, somewhere between 0.1 and 1%. And then the bandwidth, well, that's, yeah, how long is a piece of string? Anywhere from 384 kilobits to 20 megabits. Okay, data applications that have no tolerance for data loss, such as email and web pages, and so they use TCP to ensure that if packets are lost in transit, they will be resent. It can be smooth or bursty. Network traffic control is usually smooth and predictable. Some TCP applications consume a large portion of the network capacity. FTP will consume as much bandwidth as it can get when you download a large file, such as a movie or a game. So it can be smooth, but also bursty. It can be benign or greedy. It's drop insensitive. It's delay insensitive. And TCP, of course, tidies up the mess. So data traffic is relatively insensitive to drops and delays compared to voice and video. Quality experience is important to consider with data traffic. Does the data come from the interactive application? Is the data mission critical? And so basically you got factors like interactive and non-interactive. If it's mission critical, of course, you'd have to prioritize traffic. If it's delay can vary greatly as long as necessary minimum bandwidth is supplied. Not mission critical, while things are better with less delay, of course, and gets any leftover bandwidth after voice and video and other data application needs are met. So yeah, data transfer is certainly flexible. All right, queuing algorithms. So the QoS policy implemented by the network administrator becomes active when congestion occurs on the link. Queuing is a congestion management tool that can buffer, prioritize, and if required, reorder packets before being transmitted to the destination. So there's several algorithms available. There's first in, first out. There's weighted fair queuing. There's class-based weighted fair queuing, and there's low latency queuing. We'll talk about those in the coming slides. So first in, first out is basically no priority at all. And so basically first in goes to the front of the queue, and so it will be the first one delivered. So no content of priority or classes of traffic, and consequently makes no decision about packet priority. There is only one queue and all packets are treated equally. Packets send out an interface in the order in which they arrive, basically. So yeah, if there's no congestion, it's not a problem. If there is congestion, it can be a problem. All right, so there's weighted fair queue. And so that's an automated scheduling method that provides fair bandwidth allocation to all network traffic. And so it applies priority or weights to identified traffic, classifies it into conversations or flows, and then determines how much bandwidth each flow is allowed relative to the other flows. Weighted fair queue classifies traffic into different flows based on source and destination IP address, MAC addresses, port numbers, protocol, and type of service value. It is not supported with tunneling and encryption because these features modify the packet content information required by weighted fair queue to make its classifications. Now, class-based weighted fair queue. Now, this one basically, if you're talking about serial interfaces, it's actually on by default if you've got an interface slower than T1 or 1.544, which is the assumption for your serial interfaces anyway. And so if you've got a slower interface, it will run weighted fair queue. If it's faster, it will use FIFO by default. Now, of course, you can change what queuing algorithm is used. And so for a completely automated system, weighted fair queue does work well. Really, you only need the other ones if you've got some specific needs that weighted fair queue will not meet. And so this is when you go into class-based weighted fair queuing. Extends the standard weighted fair queue functionality to provide support for user-defined traffic classes. So as it said before, the other one is completely automatic. Normally it does make sensible decisions, but well, you know, it can't be right all the time. So traffic classes are defined based on match criteria, including protocols, access control lists, and input interfaces. Packets satisfying the match criteria for a class constitute the traffic for that class. A FIFO queue is reserved for each class, and the traffic belonging to a class is directed to the queue for that class. The class can be assigned characteristics such as bandwidth, weight, and maximum packet limit. The bandwidth assigned to a class is the generated bandwidth delivered during congestion. Packets belonging to a class are subject to the bandwidth and queue limits, which is the maximum number of packets allowed to accumulate in the queue that characterise that class. All right, so after a queue has reached its configured queue length, adding more packets to the class causes a tail drop or packet drop to take effect, depending on how class policy is configured. Tail drop discards any packet that arrives at the tail end of a queue that has completely used up its packet holding resources. This is a default queuing response to congestion. Tail drop treats all traffic equally and does not differentiate between classes of service. And so we've got these different classes, the packets arrive, and basically, yeah, because of enqueued, class 1 will actually get first dibs, then class 2, and then class 3 will get the rest. Okay, did I miss a slide? No, I didn't, sorry. Flickering and I'm not happy, but anyway. The low latency queuing feature brings strict priority queuing to CBWFQ, and so strict PQ allows delay sensitive packets such as voice to be sent before packets in other queues. It allows delay-sensitive packets such as voice to be sent first before packets in other queues, giving delay-sensitive packets preferential treatment over other traffic. Cisco recommends that only voice traffic be directed to the priority queue. So again, sort of building on CBWFQ again. All right, QoS models. All right, selecting an appropriate QoS policy model. So there are 3 service models for QoS. It's implemented in a network using either int services or differentiated services. Int service provides the highest guarantee of QoS. It is very resource intensive and therefore not easily scalable. Diff-serve is less resource intensive and more scalable. Int-serve and diff-serve sometimes co-deployed in network QoS implementations. So this best effort model, not an implementation of QoS, is not explicitly configured, used when QoS is not required. So best effort is basically FIFO, we haven't done anything. Then there's integrated services and differentiated services. So integrated services provides very high QoS to IP packets with guaranteed delivery, defines a signaling process for applications to signal to the network that they require special QoS for a period and that bandwidth should be reserved, and can severely limit the scalability of a network. With differentiated services, provides highly scalable and flexible in implementing QoS. Network devices recognize traffic classes and provide different service levels to different traffic classes. Okay, so the basic design internet is best effort packet delivery and provides no guarantees. The best effort model treats all network packets in the same way. So an emergency voice message is treated the same way as a digital photograph attached to an email. Benefits and drawbacks of the best method model, of course, it's the most scalable one because there's very little effort put into it. Scalability is only limited by available bandwidth, in which case all traffic is equally affected. No special QoS mechanisms are required. It is the easiest and quickest model to deploy. Of course, the drawbacks are there are no guarantees of delivery. Packets will arrive whenever they can and in order possibly if they arrive at all. No packets have preferential treatment. Critical data is treated the same as casual email is treated. All right, so integrated services delivers the end-to-end QoS that real-time applications require. It explicitly manages network resources to provide QoS to individual flows or streams, sometimes called microflows. Uses resource reservation and emission control mechanisms as building blocks to establish and maintain QoS. Uses a connection-oriented approach. Each individual communication must explicitly specify its traffic descriptor and requested resources to the network. The edge router performs admission control to ensure the available resources are sufficient in the network. So with integrated services, the application requests a specific kind of service from the network before sending data. The application informs the network of its traffic profile and requests a particular kind of service that can encompass its bandwidth and delay requirements. Integrated services uses resource reservation protocol, or RSVP, to signal the QoS needs of an application's traffic along devices in the end-to-end path through the network. If network devices along the path can reserve the necessary bandwidth, the originating application can begin transmitting. If the requested reservation fails along the path, the originating application does not send any data. All right, so what's good about it? The explicit end-to-end resource admission control, per request policy admission control, and signaling of dynamic ports. Drawbacks, resource intensity due to the stateful architecture requirement for continuous signaling. Flow-based approach, not scalable to large implementations such as the internet. All right, with differentiated services, QoS model specifies a simple and scalable mechanism for classifying and managing network traffic. It is not an end-to-end QoS strategy because it cannot enforce end-to-end guarantees. Hosts forward traffic to a router which classifies the flows into aggregates or classes and provides the appropriate QoS policy for the classes. It enforces and applies QoS mechanisms on a hop-by-hop basis, uniformly applying global meaning to each traffic class to provide both flexibility and scalability. It divides network traffic into classes based on business requirements. Each of the classes can then be assigned a different level of service. As the packets traverse a network, each of the network devices identifies the packet class and services the packet according to that class. It's possible to choose many levels of service with differentiated services. So the benefits, it's highly scalable, provides many different levels of quality. There is no absolute guarantee of service quality and requires a set of complex mechanisms to work in concert throughout the network. All right, implementation techniques. So avoiding packet loss. Packet loss is usually the result of congestion in an interface. Most applications that use TCP experience slowdown because TCP automatically adjusts to network congestion. Drop TCP segments cause TCP sessions to reduce their window sizes. Some applications do not use TCP and cannot handle those drops. They're fragile flows. The following approaches to prevent packet drops in sensitive applications. Increase link capacity to ease or prevent congestion. That's the easy but more expensive way to do it. You can guarantee enough bandwidth and increase buffer space to accommodate bursts of traffic from fragile flows. Weighted fair queue, class-based and low LLQ can guarantee bandwidth and provide prioritised forwarding to drop sensitive applications. You can drop lower priority packets before congestion occurs. iOS QoS provides queuing mechanisms such as weighted random early detection that starts dropping lower priority packets before congestion occurs. And so, of course, again, that will prompt TCP to decrease window sizes and hopefully slow down flows and decrease the chance that the congestion will happen at all. Okay, so what tools are there? And so there's three classifications of tools. So there's classification and marking tools, and congestion avoidance tools, and congestion management tools. So with the marking tools, sessions or flows are analysed to determine what traffic class they belong to. When the traffic class is determined, the packets are marked. So you've got your headings, your IP header as that information. All right, congestion avoidance tools. So traffic classes are allotted portions of network resources as defined by the policy. Policy also identifies how some traffic may be selectively dropped, delayed or remarked to avoid congestion. And so we can use that WRED that we were talking about in the previous slide, and is used to regulate traffic, TCP data traffic in a bandwidth efficient manner before tail drops caused by queue overflows. Congestion management tools. When traffic exceeds available network resources, traffic is queued to await availability resources. And so common management tools include your queuing algorithms, basically. So the figure shows the sequence of QoS tools used when applied to traffic or packet flows. Ingress packets are classified and their respective IP header is marked. To avoid congestion, packets are then allocated resources based on defined policies, and then the packets are then queued and forwarded out the egress interface based on their defined QoS shaping and policing policy. Now, classification and marking can be done on ingress or egress, whereas other QoS actions such as queuing and shaping are usually done only on egress. All right, before a packet can have a QoS policy applied to it, the packet has to be classified. Classification determines the class of traffic to which packets or frames belong. Only after traffic is marked can policies be applied to it. So methods of classifying traffic flows at layer 2 and layer 3 include using interfaces, ACLs and class maps. Traffic can also be classified using layers 4 through to 7 using network-based application recognition. How traffic is marked usually depends on the technology. The decision of whether to mark traffic layer 2 or 3 or both is not trivial and should be made after consideration of the following points. Layer 2 marking of frames can be performed for non-IP traffic. Layer 2 marking of frames is the only QoS option available for switches that are not IP aware. Layer 3 marking, of course, will last longer. It will be carried end to end because, you know, layer 2 headers are stripped and remade at layer 3 boundaries. So you've got COS fields and 802.1Q and P. Wi-Fi, you've got a traffic identifier. MPLS has got experimental entries. And of course, you've got IP precedence and differentiated services on IPv4 and IPv6. Now, marking at layer 2. And so typically it's we've looked at 802.1Q when we've spoken about inter-VLAN routing. Well, basically, it's an extra part of a header that's added. When 802.1Q is implemented, 2 fields are inserted into the Ethernet field. And so you've got your priority field here, and then you've got the VLAN ID later. Also includes QoS prioritization scheme, which is known as 802.1P. The standard uses 3 first bits of the tag control information field known as the priority field. This 3-bit field identifies the class of service. This means that layer 2 frame can be marked with 1 of 8 levels, so 0 through to 7 because you've got 3 bits. And so 0 means best effort, and then you've got 5, which is voice, and which is your highest priority, and 6 and 7 aren't in use at the moment. With layer 3, you've got type of service in IPv4 and traffic class in IPv6. They do much the same thing, just different names. Both support the 8-bit field for that marking. So in there, they carry the packet marking as assigned by the QoS classification tools. So there's RFC 791, which is a 3-bit IP precedence field to be used for QoS markings. There's RFC 2474, which supersedes 791 and redefines the TOS field by renaming and extending the field to 6 bits. And so the differentiated services code point field, these 6 bits offer a maximum of 64 possible classes of service. The remaining 2 IP extended congestion notification bits can be used by ECN aware routers to mark packets instead of dropping them. So with that, of course, best effort is of course no priority at all, and so again that's value is 0. Expedited forwarding has a value of 46, and then assured forwarding defines AF to use the first 5 most significant bits to indicate queues and drop preference. Okay, so DSCP values, assured forwarding values are shown in the figure, and so the AFXY formula is specified as follows. The first 3 most significant bits are used to designate the class. Class 4 is the best queue, and class 1 is the worst queue. The 4th and 5th most significant bits are used to designate a drop preference, and the 6th most significant bit is set to 0. So, for example, AF32 belongs to class 3 and has a medium drop preference. Class selector bits. So the first 3 most significant bits of the field indicate the class, and so again they map directly to the 3 bits of the COS field and the IPP field to maintain compatibility with 802.1p. So again 0 through to 7. Trust boundaries. Traffic should be classified and marked as close to its source as technically and administratively feasible. This defines the trust boundary. Trust endpoints have the capabilities and intelligence to mark application traffic to the appropriate layer 2 COS or layer 3 DSCP. And secure endpoints can have traffic marked at layer 2 switch. Traffic can also be marked at layer 3 switches and routers. So congestion avoidance tools monitor traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks before congestion becomes a problem. They monitor network traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks. They monitor the average depth of the queue. When the queue is below the minimum threshold, there are no drops. As the queue fills to the maximum threshold, a small percentage of packets are dropped. When the maximum threshold is passed, all packets are dropped. Some congestion avoidance techniques provide preferential treatment for which packets get dropped. And so you've got weighted random early detection, allows for congestion avoidance on network interfaces by providing buffer management, allowing TCP traffic to decrease or throttle back before buffers are exhausted. WRED avoids tail drops and maximizes network use and TCP-based application performance. All right, shaping and policing. Shaping and policing are 2 mechanisms used by QoS software to prevent congestion. So traffic shaping retains excessive packets in a queue and then schedules the access for later transmission over increments of time. Traffic shaping results in a smooth packet output rate. Shaping is an outbound concept. Packets going into an interface get queued and can be shaped. In contrast, policing is applied to inbound traffic on an interface. Policing is applied to inbound traffic on an interface. Policing is commonly implemented by service providers to enforce contracted customer information rate, or CIR. Here, however, the service provider may also allow bursting over the CIR if the service provider's network is not currently experiencing congestion. So that's very much the story of how frame relay worked back in a few years ago. Now, QoS policy guidelines. QoS policies must consider the full path from source to destination. A few guidelines that can help ensure the best experience for end users includes the following. Enable queuing at every device in the path between source and destination. Classify and mark traffic as close to the source as possible. Shape and police traffic flows as close to their sources as possible. Okay, we've hit the end of the chapter, so we've just got the summary. So voice and live video transmissions create higher expectations for quality delivery among users, create a need for quality of service. Without any QoS mechanism in place, packets are processed in the order in which they are received. When congestion occurs, network devices such as routers and switches can drop packets. Without any QoS, time-sensitive packets such as real-time video and voice will be dropped with the same frequency as data that is not time-sensitive, such as email and web browsing. Queuing packets causes delay because new packets cannot be transmitted until previous packets have been processed. Two types of delays are fixed and variable. Sources of delay are code delay, packetization delay, queuing delay, serialization delay, propagation delay, and de-jitter delay. Jitter is the variation in the delay of received packets. Voice and video traffic are two of the main reasons for QoS. Voice traffic is smooth and benign, but it is sensitive to drops and delays. Voice can tolerate a certain amount of latency, jitter and loss without any noticeable effects. Video traffic is more demanding than voice because of the size of the packets it sends across the network. Video traffic is bursty, greedy, drop sensitive and delay sensitive. Data traffic is not as demanding as voice and video. Data packets often use TCP applications which can retransmit data and therefore are not sensitive to drops and delays. The QoS policy implemented by the network administrator becomes active when congestion occurs on the link. Queuing is a congestion management tool that can buffer, prioritise and if required reorder packets before being transmitted to the destination. FIFO queuing buffers and forwards packets in the order they arrive. FIFO has no concept of priority or classes of traffic and consequently makes no decision about packet priority. Weighted fair queue is an automated scheduling method that provides fair bandwidth allocation to all network traffic. It applies priority or weights to identify traffic and classifies it into conversations or flows. Class-based weighted fair queue extends the standard WFQ functionality to provide support for user-defined traffic classes. You can define traffic classes based on match criteria, including protocols, access control lists, and input interfaces. LLQ feature brings strict priority queuing to CBWFQ. There are three methods for implementing QoS. Best effort, which is no queuing, no control, integrated services and differentiated services. Integrated services architecture was developed to meet the needs of real-time applications such as remote video, multimedia conferencing, data visualization applications and virtual reality. But of course it's not quite so scalable. Differentiated services specifies a simple and scalable mechanism for classifying and managing network traffic. It overcomes the limitations of both best effort and integrated services. There are three categories of QoS tools: classification, marking, then congestion avoidance, and then congestion management. Classification determines the class of traffic to which packets or frames belong. And so they can either be on layer 2 or layer 3, again using ACLs, interfaces and other such things like that. Traffic can also be classified on their application layers and above. Congestion management includes queuing and scheduling methods where excess traffic is buffered or queued and sometimes dropped while it waits to be sent out egress interface. Congestion avoidance Tools help to monitor traffic loads in an effort to anticipate and avoid congestion at common network and inter-network bottlenecks before congestion becomes a problem. Cisco IOS QoS includes weighted random early detection as a possible congestion avoidance solution. That is the end of the chapter. So next time it'll be module 10. See you then.